So here in this question, we're told that the weights of the contents of breakfast cereal boxes are normally distributed. A manufacturer changes the style of the boxes, but claims that the weight of the contents are going to remain the same. Now, a random sample of 6 of the old style boxes have contents that have the following weights. So we have this data set. We're then told that the weight Y grams of the contents of an independent random sample of 5 new style boxes gave these summary statistics. We've got Y bar and we've got the sample standard deviation S. The first thing we're asked to do is to use a two-tailed test to show that at the 10% level of significance that the variances of the weights of the contents of the old and the new style boxes can be assumed to be equal. So here we're testing whether the variances are going to be the same. So we're going to do an F distribution test. But before we can do that, I'm going to need to get some summary statistics. I need to know the sample variance for both the old boxes and the new boxes. So let's actually start to get some of that data together. We know that there are 6 of the old style box in the sample. So we can say NX equals 6. And the mean we can calculate. This should really go into a calculator, list 1 and list 2. And we get an answer of 509.83. I always like to show the sum of those values divided by n. So we should now be able to find the sample standard deviation. So S of x is going to be n over n minus 1. And we're going to have the sum of x squared over n, subtract the mean squared. Okay, let's just substitute in the values that we know. Once again, these will come from putting the data into the table. On the summary screen, I can get the sum of x squared, which is 1,559,691. So just putting in all the values that we'd found earlier, we get 4.7081. So that's going to be S for the x values. We were given some of the y values, so I'm just going to summarize them all here. Sample size of 5, y bar is 504.8, and S is going to be 3.42. Okay, so we should now be able to start the hypothesis test. As always, we'll get the hypotheses down. So sigma, so the variance of x equals the variance of y, and the alternate hypothesis, the variance of x does not equal the variance of y. So this is a two-tailed test. So alpha over 2 equals 0.05. Let's find the critical value that we're going to work with. Critical value is going to come from the F distribution, and the parameters in the F distribution are going to be nx minus 1 and ny minus 1. One smaller than the sample size in each of those cases. So just looking this up in the tables, and we get 6.26. So where would this be on a diagram? So over here in the right-hand tail. Let's calculate the test statistic. The test statistic comes from s squared x over s squared y. So just plugging these values into the calculator, and we get 1.8952. Now this is not significant. It's not inside the critical region. We do not have a significant result. 1 would be the optimal answer. That would mean that the variances were exactly the same. The two sample variances were exactly the same. But we don't have that. We have 1.8952, which is less than the critical value. It's not inside the critical region. Okay, so just our conclusions as always. 1 mathematical and 1 in context. So firstly, there is not enough evidence to reject H0 since we did not have a significant result. And here we can say that there is evidence to suggest that the variance of the weights of the new style cereal box is actually the same as the variance of the weights of the old style cereal boxes. In part B, we've been asked to find the 90% confidence interval for mu x minus mu y, so the difference between the means. Okay, so for this confidence interval, there's a couple of things that we need to bear in mind. Firstly, the critical value. Is it going to come from the normal distribution, or is it going to come from the t distribution? We're going to be using the t distribution since we do not know the variance of the original distribution and we have a very small sample size. Secondly, we've just tested and shown that the variances are going to be the same. or at least we can assume the variances are going to be the same. So for the variance or the standard deviation, we're going to need to pool those variances together. So we're going to calculate a pooled variance in this instance. Okay, so the 90% confidence interval is going to take this form. So x bar minus y bar plus or minus our critical value multiplied by s, the pooled standard deviation, multiplied by the root of 1 over nx plus 1 over ny. So this standard deviation expression, this expression for the spread, that's always going to be able to be found in your formula booklet, but something with enough practice you'll commit to memory. Okay, now let's actually find that pooled variance. So, just recalling this formula, it's going to be s squared x multiplied by nx minus 1 plus s squared y over ny minus 1 over the two sample sizes added together, subtract 2. Substitute in the values that we know, and that gets us a pooled variance of 17.5130. Now let's substitute into the confidence interval. So 509.83 minus 504.8, so those were the two sample means, plus or minus the critical value, and we're going to multiply by the root 17.5130 and root 1 over 6 plus 1 over 5. Okay, this will just go straight into the calculator, and I'll produce these two limits of the confidence intervals, these two boundaries of the confidence interval. 0.385, 9.675. Part C of the question. We're told, with reference to the confidence interval, comment on the manufacturer's claim. Well, the manufacturer was claiming that the variance would be unchanged. Well, the manufacturer is claiming that the weight of the contents is going to remain the same. Well, our confidence interval for the difference between the old weight and the new weight, both of these limits are positive. So this actually shows that the old weight minus the new weight gives a positive value, as in the old mean weight is higher than the new mean weight. If we wanted to show they were the same, we would have needed a 0 in between the boundaries of this confidence interval. But since it wasn't in the interval, we can conclude that the manager's claim that the weight is unchanged is incorrect. We can reject that claim from the manager.